I mean, my concern about QFT2 is mainly how much you will benefit from QFT1. Most of you are master students who didn't even take quantum mechanics 1. Okay, so last week, the last thing we were doing was we were looking at some process where two particles, K1 and K2, became two particles with different momenta. And in our model, the interaction terms were given by, let's say, minus lambda d cubed r, first kind of particle, second kind of particle, again, first kind of particle. We have such an interaction. And we were basically doing just what Schwarz calls old-fashioned perturbation theory. We were looking at some transition amplitudes from the initial state to the final state, and the general expression was given by this formula, this expression, plus sum over all possible intermediate states different from the initial state of V, F, N, 1 over the initial energy, the final energy, V, and E, plus, of course, there were higher order terms, and here EI and EN are basically, let me write it this way, our Hamiltonian has two parts, H0 plus V. H0 is the part that we can actually solve, V is the part we cannot exactly solve, we treat it as a perturbation, and so in our case this is our minus V. And these energy states, H0 acting on the initial state, gives us EII. It's not H acting on I, it's H0 acting on a given state, gives the energies EI. And then we said that in principle, this sum over N over here goes over all states. Now, in this case, we have states with different momenta, states with different number of particles, etc. All of them are summed over. But then, since our V is given by this form, you see each one of those operators, as phi I, can be written as d cubed p divided by 2 pi cubed, 1 over square root of 2 omega p. A of p of the ith type of particle, e to power I p dot r, plus a dagger for the ith type of particle with momentum p, e to power minus I p dot r. So each of these phi's, when acting on a state, either creates a particle or destroys a particle. So you see, if when you are calculating this V and I, this is our V, so phi 1 creates a particle or destroys one of the existing particles, phi 2 creates a particle or destroys one of the existing particles of type 2. Again, this phi 1 creates or destroys one of the existing particles on the state that it acts on. So in our initial state, this one, there are no phi 2 type of particle. So the only thing phi 2 can do is create one phi 2 kind of particle. But this product of two phi 1 fields, this one and this one, if you consider the product, I can have both creation operators from both of them, which will increase the number of particles by 2. I can take the annihilation operator from each one of them, which will reduce the number of type 1 kind of particles by 2. Or I will have mixed term. I will get the annihilation operator from one of them, the creation of operator from the other one of them, which will annihilate one kind of particle, one of the existing type 1 particles, and create a new type 2 particle. So although I have a sum over all possible states, not all of them contribute. Only the ones that will contribute will be, first of all, phi 2 will definitely need to create a phi 2 kind of particle with some momentum, let's say, k5. If I take the annihilation operator, the creation operator from both of the phi 1 fields, then I will have an additional, well, let's say, I will have an additional k3 and k4. These are in addition to the already existing ones. So this is one possible intermediate state. Another possible intermediate state will be, I definitely have this phi 2, type 2 kind of particle, and but type 1 particles are both annihilated. So you see, I take the annihilation part of these phi 1 fields. They have to annihilate the two particles I have in my initial state. Over here, there is no particle of type 1 left, but there's a particle of type 2 created by this phi 2. That's another possible intermediate state that will contribute to my sum. And another one will be, well, I should have a phi 2 kind of particle, that is for sure, that is almost given. But one of the existing particles is annihilated. A new one is created. Let me call that K3, K1. You see, K2 is annihilated, K3 is created. Well, there are other combinations of such states. And, well, basically, those are the three kinds of states that will appear in my sum. And we were just trying to calculate the contributions of these terms. Diagrammatically speaking, I said that, okay, if this is K1 and K2, this vertical line just shows me the V, action of V. V will create K3, K4, and K5. K1 and K2, it doesn't do anything on them. Then I will have another V, action of the other V. Remember, I have two V's here. One is this one, the other one is over here. That other V should destroy, annihilate two of these momenta. No, three of these momenta, in fact. So you see, these will be annihilated, this one, and this one, because they have to be annihilated because in my final state I have different momenta. So this K3 and K5 has to be P1 and P2. This is one possible contribution to my sum. Now I will plot these slightly differently. You see, if you look at my potential, all the fields are at the same point. To emphasize that, rather than drawing these diagrams like this, I will draw it slightly differently. You see, these two are annihilated over there. This photon is also, this other particle is also annihilated there. Over here, I have two particles created. So if you like, these are what I call the action of V's. This is one possible contribution. Another contribution we looked at was I have these two kinds of particles. At this point, they are both annihilated. And the second kind of particle is created. At the second potential, well, this second kind of particle should be annihilated because I don't have it in the final state, but two other particles are created. Again, this one I will show in this way. And then the other kind of intermediate states, here I will have, let's say, two particles are arriving. One of them will be annihilated. Another one will be created. And the second kind of particle will be created. And the second kind of particle will be annihilated afterwards. Okay, these are created here. The second kind of particle will be annihilated by the second potential. And this field that we didn't touch before, I mean, in the final state, I don't have such a particle of that momentum. So that has to be annihilated. Another type 1 kind particle is created. This is K1, K2. This will be P1 and P2. Again, diagrammatically, I will show it as, okay, the other one is, okay, this is that diagram. And then I have another diagram of this form. Now, basically, they are the same diagram, just exchanging the particles. So these are all the contributions. Now we have to, of course, calculate them. Any questions up to here?
What is it that we're going to calculate now?
Well, we will calculate this transition matrix element. Why are we interested in? Well, that's what we usually observe. We create some initial state and see how it evolves. But I have to emphasize that here we are doing time-independent perturbation theory. We are not looking at time-dependent one. We will do that later, after this one. Okay, before we continue, let me just share one of my experience about students coming to lectures. You see, it happens that sometimes I come to the class and there's no one during the lecture hour. Of course, when I talk with the students, all of them have an excuse. They forgot, they had to go somewhere, they missed the bus, the car broke down, etc. Then I say that once the door is closed, no one should enter. And by some magic, all the problems disappear. If you can solve your problems, solve them without me imposing that rule. So it might really happen that you were late that time, you had an excuse, but if it happens to, I don't know, all of you except 3 of them, there is something else there, so don't do it. I mean, I believe it's rude to your classmates who were here on time. As I said, I have heard many excuses which magically disappear once I implement that rule.
No magic can solve this.
You know, my experience is, yeah, there is a magic that can solve. Anyway, back to the lecture. Now we will calculate. Okay, these are just the grammatical representation of mathematical expressions. But at the end of the day, we need to calculate and simplify our own mathematical expressions. So we need to calculate them. Now, if you remember how we calculated them, let's look at, we already looked at, well, this one. Well, I wouldn't like to deal with states with 5 particles, so let me look at these contributions. Intermediate state contains 1 second type of particle and 2 first kind of particle. So this is, let me calculate this one. K1 prime, K2 prime, phi K5. V K1 and K2. And we know what V is. And of course, in my summation, I will end up having, I need to sum over all possible values of k1 and k2 prime, k1 prime and k2 prime. So what we how we evaluate this sum? Well, we can write it explicitly. Let me first write it explicitly. I know what my states are. AK1, type 1, AK2, this is second type of, first kind of particles, AK5, second kind of particles, and I have the normalization, twice omega K1, twice omega K2, twice omega K3.
Do we need primes on that case?
Yes. These are all under the square root. That's how I define my state. This state is defined by this operation. So these A's acting on the bras, they act like creation particles, so they create particles in the bras. That square root of 2 omega k's are my normalization convention. And then I have and then twice omega k1 So I didn't even write explicitly what phi 1 and phi 2 is. Things get a bit cumbersome. So let me do some simplifications.
Shouldn't we write for phi k5 an integral term, but we just write it as if it is just a very factor?
No, not here. You see, this state. Okay, this notation is, sometimes I will also use this notation. What this means is I have one phi 1 kind of particle with momentum k1 prime, one phi 1 type of particle with momentum k2 prime, and one type 2 kind of particle with momentum k5. So those phi's are not actually the fields themselves. They're just denoting the kind of particle I have, 1 and 2. So this is defined as a dagger of kind 1 particles with momentum k1 prime, a dagger with of kind 1 particle with momentum k2 prime, a dagger for the creation operator for the second kind of particle with momentum k5 acting on vacuum, and then I also have this normalization. These are the notations I will be using. Well, since most of the time I will have particles of type 1, I don't write phi 1 or for them. So whenever you see just the momentum, I will just interpret it as the kind 1 particle. And for the second kind of particle, I explicitly put the phi there. So how will I calculate this? Well, basically, what I will do is I will take, let's say, this operator, commute it all the way through phi 1, phi 2, this phi 1, and all these creation operators, and act it on the vacuum. That will give me 0. So I will have these commutators all the time. And eventually, the commutators will have non-zero contribution to my final result. But when A reaches the vacuum on the right, it will annihilate the vacuum. I don't have any contribution. But since it's the second kind of particle, it will commute with phi 1. This phi 1 and this phi 1, it will commute with these creation operators. It will commute with everything, except then this phi 2. I don't have to write it down explicitly, but it's enough for me to calculate the commutator of A2 with phi 2 only. That will be the only term that is contributing. Again, I will even use a better shortcut. I will show this as K1 prime, K2 prime, phi of K5. Let me call K1 and K2. I will just show that the operator that creates this particle of momentum K5 will commute with this phi 2 at the R field. This will be the notation I will be using. Again, the meaning of that thing is just go back to this expression over here. As I'm commuting this A2, K5 with all the other fields, this is the contribution I will get when the creation operator for this field commutes with this one. Well, of course, there are other commutators, but they will give me 0. Let me calculate that commutator explicitly. Just that one. I'm not writing the other fields, other operators. There's also K1 and K2 particles next by this phi K5, but they will not affect my computation. So I'm just not writing them. They are there. Well, this will be vacuum AK5 for the second kind of particles, square root of 2 omega K5. Now, phi 2 field will be d cubed p divided by 2 pi cubed, 1 over square root of 2 omega p. And the one term that will contribute, well, let me also add the zero here. Again, I repeat, I have all the other terms, but they will not change my computation. The only part that will contribute to this contraction, so-called, this will be called a contraction, will be the one that contains a dagger of P with the phase factor e to power minus I P dot R acting and vacuum. This is the only term that will contribute. Which will be equal to, well, let me just take out all the numbers. The commutator is just a number. It's not an operator, so I can also take it out of that matrix element. That vacuum matrix element is 1. So after all this computation, what I see is phi of K5, phi 2. This contraction will be, well, this is nothing but 2 pi cubed, the 3-dimensional Dirac delta of K5 minus P. So I can evaluate the P integral. Well, the P integral just tells me that wherever I see P, I should replace with K5. But then this 2 omega K5 square root and this 2 omega P under the square root, they will cancel. These 2 pi cubes, they will cancel. And I will end up having just e to the power minus I K5 times R. Well, you see, AK5 to a dagger P. Well, okay, there are two things. Well, let me write it explicitly. This is equal to AK5 to AP dagger minus AP dagger, AK5, 2. Well, these are 2, by the way. I'm only writing the operators for the second kind of field, plus AP2 dagger, AK5, 2. But this gives me 0. This doesn't contribute. Well, you can say that creation operator acting on the vacuum from the right is 0, or annihilation operator acting on the left is 0, on vacuum is 0. So the only thing that remains is this commutator, which is a number, so I can take it out of the matrix element. So at least it simplified my computation significantly. So all this thing is actually just an exponent.
Well, it is expected. It is projection of momentum state to the Polish state.
Yeah.
We could direct write it.
No.
No?
No. Well, let's go back then.
May I ask a question?
Sure.
How did you select that with this construction will be the only meaningful contribution to that whole thing, so that
I didn't calculate the whole thing yet. But what I did was, I'm always keeping this expression in my mind. And what I'm doing is I'm trying to calculate this matrix element by just commuting moving all the annihilation operators to the right and creation operators to the left. I should move A2, K5 all the way to the right. And as I'm moving it all the way to the right, I should consider the commutator with phi 2. That I have only calculated that term. So basically what I had shown is this matrix element this is equal to lambda e to power, well, let me write the r integral out, lambda d cubed r e to power minus I k5 dot r k1 prime k2 prime phi 1 of r phi 1 of r k1 k2. This is the only thing I showed. So I'm also looking for a particular contribution. You see, what happened? This phi 2 field basically annihilated this phi field in the final state, in the bra. Now, to get a non-trivial contribution, what I should do is, okay, I can have this phi 1 annihilating this chi 2 prime. And if I choose this phi 1, the other phi 1 eliminates this chi 1 prime, I get 0, because in the bra I will have vacuum. As the ket, I have a state with 2 particles. I don't get any contribution there. The only possible contribution will be if that other phi 1 annihilates one of the initial states. So what that means by this contraction is, remember, this K1, this state is a K1 dagger, K2, twice omega K1. So this contraction basically means that this as I'm moving this annihilation operator all the way to the left, I will be commuting this one with many other terms. In fact, I need to consider all possible combinations because I have to commute it with everything. This is the contribution that I will get only when that A dagger K1 commutes with that particular phi 1. Of course, that's not all the contributions. You see, this is one contribution I will get. Another contribution I will get will be this one, this phi 1 and this k1. I get that commutator, and this other phi 1 commutes with this k1. And what else do I have? I have phi 1 and k2 prime, and this phi 1 and k2. And phi 1 and k1 prime, the other phi 1 and k2. I have 4 contractions. When I'm calculating all these possible commutators, I will have these 4 terms that will give me non-zero. Well, let's see. I have already calculated what happens when I contract a field with one of the particles in the bra. Let me see what I get when I contract the field with one of the particles in the ket. So this is phi 1 of r, k1. Again, I have other particles in my kets, but I don't care about them for the time being. They will not change my computation. This will be d cubed p divided by 2 pi cubed, 1 over omega, twice omega p, a of p, e to the power minus I, sorry, here I had a dagger, sorry, let me just make a correction. A dagger comes with the positive exponent. So this is plus. A annihilation operator comes with the negative exponent in space components. And k1 is square root of 2 omega k1, a dagger k1 acting on vacuum. Again, when I commute them, the annihilation operator acting on vacuum will give me no contribution. So this will be equal to d cubed p divided by 2 pi cubed, 1 over square root of 2 omega p, square root of 2 omega k1, e to the power minus I p dot r, a of p, a of k1 dagger. Again, this commutator is 2 pi cubed, Dirac delta cubed, p minus k1. And that Dirac delta basically tells me that wherever I see p, I should replace it with k1. So these cancel, these 2 pi cubes cancel, and I end up having e to the power minus I p dot r acting on vacuum. Okay, let me put the vacuum over here also. Because I have another contribution where I have a dagger here. So that will create a 2-particle state, but what I'm interested in is only the contribution that I will get when I annihilate that particle. That is my intermediate state. No, not P, K1. So these are the matrix elements I will need. So now let's go back. I'm writing this matrix element. I had already shown that that matrix element is equal to this one. E to the power minus I k5r is from the phi 2 field. Now I have those 4 contributions. Well, let me write them out explicitly. Equals lambda d cubed r e to the power minus I k5 dot r. And this is also plus. because of the change in sign. This is plus. This is that plus over here. So let's see. This contraction, phi 1 with k2 prime, gives me e to the power plus I k2 prime r. This other phi 1 with k1, that will give me minus I k1 dot r. That's the contribution I will get from these two contractions. Again, whenever I say contraction, just remember I'm just commuting all these operators left and right, and these are the ones that will give me non-zero contribution. Let me look at this contraction. It will give me, that is another term, it will give me e to the power I k1 prime dot r. And then this contraction will again give me e to the power minus I k1 dot r. Now I'm looking at this contraction, that will be plus e to the power I k2 prime dot r. And this one is minus I k2 dot r. And finally, I have this one is e to the power I k1 prime dot r, and this one is e to the power minus I k2 prime dot r. Those are the four contributions I have. But now the integral is almost trivial. It will just give me Dirac deltas. So let's see, this is lambda times 2 pi cubed Dirac delta, the three-dimensional Dirac delta of k5 plus k2 prime sorry, let me just make one more correction to all these terms. You see, in the first term, these are these two contractions. What is left is k1 prime, k2. Those states are still there. They are not contracted with anything else in that term. Then I have this second contribution, which was from these two contractions. What are left is k2 prime, k2, and then the third term was from these two contractions. What is left not contracted is k1 prime, k2, k1, thank you. And finally, in these two contractions, what is left is k2 prime, k2.
Isn't the second term also k2 prime, k2?
You see, the second term is, yeah, it's k2 prime, k2. The second term is k2 prime, k2. And so the fourth term, no, sorry, the second term, no, the k2 prime, k1, sorry. Now I can evaluate all those integrals. So I have lambda. The first term, the r integral, will give me 2 pi cubed Dirac delta, the three-dimensional Dirac delta, k5 plus k2 prime minus k1. And that matrix element will be 2 pi cubed Dirac delta k1 prime minus k2. That's the first term. The second term will be lambda 2 pi cubed, the three-dimensional Dirac delta of k5 plus k1 prime minus k1 times 2 pi cubed Dirac delta k2 prime minus k2 plus lambda 2 pi cubed, the three-dimensional Dirac delta of k5 plus k2 prime minus k2, 2 pi cubed k1 prime minus k1 plus lambda 2 pi cubed k5 plus k1 prime minus k2 prime 2 pi cubed Dirac delta, again three-dimensional, k2 prime minus k1. So what are these contributions? You see, initial state, I have k1 and k2. And let me look at these two terms. In those two terms, the momentum of k1 is equal to one of the momentum in the final states. So k1 basically continues. So this can be k1 prime or k2 prime. It is one of the intermediate states, intermediate particles, but their momentum is the same. Which intermediate state? Well, it can be one or the other one. That's why we have two contributions. What happens to K2? K2 is equal to K1 plus K5. So let's say that this is K5, and there's some other particle of type 1, which has momentum either K2 prime or K1 prime. Let me write it that way. If K1 is equal to K1 prime, then that other particle has momentum K2 prime. And if the first particle has momentum K2 prime is the momentum of the first particle, then the other particle has momentum K1 prime. And those Dirac deltas tells me that there's momentum conservation also here.
May I ask a question?
At this vertex. Yes.
In the last summation, do we have an extra prime? Because K2 prime exists twice.
Yes. No. There is some problem in the first one. Is okay. Phi 1 is contract with K1 prime or K2.
K2, right? Not K2 prime.
That is K2. Yes.
Okay. Otherwise, they were clashing.
Yeah. No. You're right. That's still not my final state. Remember, I have another vertex to calculate. But any questions up to here? Now, keep in mind that eventually I will be summing over all K1 primes and K2 primes. Here, basically, I have these two kinds of contributions. This is K1 prime. This is K2 K5, K2 prime, plus I have K1, K2 prime, K2, this is K5, this is K1 prime. I have these two contributions. And remember, these are just these two terms. And if we go back to our general expression of perturbation theory, I am summing over all intermediate states. That means not just the number of particles, but also over their momenta. So I will be integrating over K1 prime and also K2 prime. So this summation over n, you see, for these states, sum over n would imply integral over d cubed K1, d cubed K3. But that means I can just change their names. I can, since they are just integration variables, I can call K1 prime as K2 prime and K2 prime as K1 prime in any one of these contributions. So when I sum these two, what I will obtain is I will get twice K1, K1 prime, K2, K2 prime, and this is K5. That's enough for me to calculate one of them. The other one will be exactly the same contribution.
Can I ask something? When we also consider the other vertex, you will see that free momentum is also conserved.
Which other vertex?
When gamma 5.
You are,
K5.
you see, let's look at those two terms first. You see, this diagram are these two terms. That's why I have this factor 2, because these two diagrams have exactly the same contribution. Now let's look at these ones. There what happens is K2 is one of the final momentum. One of the final momentum, K1 prime or K2 prime, is equal to K2. So those other two terms will correspond to diagrams of this sort. I will have K1, this is K2, it will be either K1 prime, and then in K1, I have K1 will emit the other particle, and it will become K2 prime. This is K5. I have momentum conservation there, and plus I will have K, this is K1, this is K1 prime, and K2, this is K2 prime. Again, I have momentum conservation there. This will be twice this diagram. Momentum conservation at those vertices. So if I just sum the contributions of these two diagrams and multiply it by 2, I get all these 4 terms. Yes?
Now that we can say that free momentum is conserved, right?
Yes?
But when we look at the form of the transfer function, the final energy cannot be equal to the initial energy.
No.
Can be.
So the intermediate energy, you see here, I'm summing over all states. There's no energy conservation for this En state, the intermediate state.
So even though we have a conserved free momentum, we don't have any conserved energy.
We will say it like that.
Okay.
You see, En need not be equal to Ei. In fact, if En is equal to Ei, it diverges.
That's actually what
Okay, you can have two meanings. One is, remember, these states that we are talking about are not energy eigenstates anyway. This I state is not an energy eigenstate. So what do you mean by energy conservation for an energy non-eigenstate?
Okay.
That is one answer. And another answer is usually makes use of the energy-time uncertainty relation. We can have energy non-conservation as long as it lasts a short amount of time. You see, this is an intermediate state. The final state, at the end of the day, we are looking at this one. The final state and in EF should be equal to EI. It's just the intermediate states doesn't have the same energy. So we say that for a short amount of time, the energy need not be conserved. So you can have energy violation as long as it lasts a very short amount of time. And in fact, that is how we also interpret, for example, photon has a very long range. Basically, because since it is massless, we can create photons of arbitrarily low energy, so the energy violation when we create a photon can be very small, so that photon can live long, meaning that it can travel a long distance. But when we look at, for example, the W bosons, they are massive. Since they are massive, they are really massive, they are like 80 times the mass of a proton, a single omega boson. So the weak interaction, since it mediates by this omega boson exchange, the energy violation is huge. Since energy violation is huge, it can only last a very short amount of time, and in that very short amount of time, omega boson cannot travel far, and hence the weak interaction has a very short range. We cannot measure the weak interactions at distances of the nuclear size. But electromagnetic interactions, in principle, it goes up to infinity. Yes?
Now, I will ask the question that I asked last week.
No, not yet. If you are asking virtual particle.
No. No, what I was asking is, when we draw these diagrams, there's this.
They are not trajectories.
Yes.
There is no time in these diagrams.
Then, how do we measure delta T?
We don't. That's just a way of making sense out of what we have found. You see, nothing in this derivation tells me that intermediate states should all have the energy. Fine. So why do you insist on energy conservation?
I don't, but
Okay,
I
so
insist on the explanation.
okay, I gave you the explanation. Forget about this. Forget about this. I am saying that energy need not be conserved into intermediate states.
Okay.
I don't like this explanation myself. But we will be doing time-dependent perturbation theory, which is the first topic in 508 quantum mechanics 2, but I will spend some time here, which hopefully will also answer your question. Any other questions before we go for a break? And by the way, I said that, okay, we have to calculate these diagrams, but we already did. I just have lambda for each one of those diagrams multiplied by momentum conservation. So hopefully the other part will be shorter. So any last questions before we go for a break?
Since we specify the final state, these diagrams just gives us all things transition from initial to final.
Yeah. You see, in our perturbative expansion, time-independent perturbation theory, you see, this was our expression. So you can interpret all these terms as saying that, okay, the initial state makes a transition to the final state by the action of V once, directly. So V just goes our initial state just to make a transition to our whatever final state we are looking at. Or we have our initial state, it makes a transition due to this V. By the way, that V is the reason why this state I is not an eigenstate, and hence it changes. It will change with time. And so this initial state might make a jump to some intermediate state N, and then that intermediate state makes another jump to the final state F. And while it is in the intermediate state N, we have this propagator, so-called. And the next term will be the initial state will make a jump to some intermediate state. That intermediate state will propagate for some time, let's say. Time in quotes, there's no time here. And then it will make a transition to some other intermediate state. And then from that second intermediate state, it will make a jump to the final state. So you can just increase the number of intermediate states you want. Each transition from one state to another state is caused by this presence of this potential.
The example B, direct solution without any approximation.
Where?
It's approximated.
Well, where is the exact solution?
Example, we say K1, K2, and we put B. So,
Sure. You see, this is my approximate expression for T. This is what I'm trying to calculate. This term is 0 because my V has to create or annihilate a particle of type 2. And in my final state, I don't have a particle of type 2. So the first term is 0, exactly 0. The second term, I now calculated this VIN. I just calculated this VIN. And that will contribute to an approximate expression of my TFI. Now let's give a 10-minute break and we will continue after the break.